Sorry about that. Didn't realize I was muted. Okay, so today we are talking about chapter 12. Chapter 12 is all about alcohols. So we're going to start off with some nomenclature. So, like I said, so our suffix for today is OL, is how we determine if we have an alcohol. Let's say we have this here, we'd have a 3-carbon chain here, so this would be a propane. But we also have an alcohol on it, so you would refer to this as a 2-propanol. With this OL suffix at the end of it. This is going to be our our highest priority group in terms of numbering things. So up till now, we've only dealt with alkenes, alkynes, and then carbon chains / halogens. As we're adding in this in, alcohols now become our number 1 position. So we're going to have alcohols. Followed by alkynes. Alkenes. And then lastly, either halogens or carbon groups. Oops. So if we have something with a both, let's say an alkene and an alcohol on there, like for instance, this compound here. Nope, sorry. This compound here, our numbering is going to favor going through the alcohol first, as opposed to going through the alkene first. So we're going to be going right to left on this one. This would be a 4-pent-ene 1 all here. When you have both, get rid of this E, make it look a little better. When you have both a alkene and an alcohol or an alkyne, you're going to list the alkene first. So the first number is going to correspond to that. And then you're going to do kind of what we're doing with when you had both an alkene and an alkyne. You'll just list another number followed by our alcohol position. Okay, let's do a more complicated one. Someone in the chat asked if you can put the 4 before. Yeah, it's much less likely to be written in this, but you could also do pent or ene 1 all, and that'd be okay also. Okay. I'm going to do just a kind of more complicated example, and then we're going to move on from nomenclature because I don't want to spend too much time on it. There's not that much different that we're doing. We just added in one more group. So For this molecule here, we are going to want to go through our alcohol first, and we still want to include our alkene chain here. So even though the longest chain you could possibly make would be 1, 2, 3, 4, 5, 6, 7 here, because this doesn't include our alcohol, we're actually going to end up going with a shorter chain because that includes both the alcohol and the alkene here. So it is a time when you can kind of break that rule of finding your longest chain when you have these higher priority groups. From here, we're doing everything we've been doing before. So you could write out what this is first. So you're going to go through your alcohol before your alkene. So this should be set up correctly. It's at 6 carbons, so it'll be a hex. Sorry, 5 hexene to all. We've got a propyl on 3. We've got 2 methyls on 4. We need to do a little bit of RNS. So our alcohol is going to be our highest priority. Followed by this right side, and then this left side. This should be clockwise. So this is going to be an R stereocenter.
There's a metal without dash or wedges. Do you put a R or S around it?
No. So if you had this here, because you don't know if it's a dash or a wedge, you're just not going to indicate it.
Okay, thank you.
Okay, so we're doing the other stereocenter. Taking a look at what we have. So we've got carbon bond to oxygen, carbon bonded to 3 more carbons, carbon bonded to 1 more carbon. So this should be our highest, followed by this here. We're also going clockwise. This should also be R. So let's put this all together. Parentheses, numerical order first. So 2R, 3R. We've got methyl. M comes before P for methyl and propyl. So 4,4 dimethyl. 3 propyl. And then our parent chain, which would be A5, hexene, 2, all here. Okay, so hopefully pretty straightforward. We basically just added in this OL concept at the end here. Tomorrow we'll do some more interesting molecules when we move on to chapter 13 and start talking about epoxides and things like that. But let's push back past nomenclature for today. We're going to talk all about making alcohols and reactions that use alcohols. So let's get started on that. The first couple of reactions that make alcohols are ones that you guys have seen a long time ago. So you have a primary halogen, and you throw in something like NaOH, or you throw in NaOH. We can do an SN2. kick out this fluorine to make an alcohol. So pretty simple reaction. We can also do an SN1 version of this. So if we had a tertiary, and we instead throw in water, we would lose our leaving group. Our water could come in. And again, we can make an alcohol this way. So these are the probably like chapter 6 or 7 versions of doing this. In chapter 8, we talked about a few other ways. So we can start with alkenes, throwing in H plus H2O. This can get us to an alcohol, as well as something like mercury acetate, water. Or if you want to do it the anti-Markovnikov way, throwing in VH3 and THF. NaOH peroxide. Gets us to our terminal one. So these are the reactions you guys know. I don't want to spend too much time on them. Let's talk about some reactions you guys haven't really talked about. And we're going to go with oxidations and reductions first, and kind of walk through some different ways to make alcohols using those. So when we're talking about oxidations and reductions, in terms of oxygen, there are 5 different states that carbon can exist in. So our completely reduced state would be this here. We have no bonds to oxygen. As we move upward, we would create 1 bond to oxygen. So we're going to have an alcohol here. This is our singly oxidized state. We can do another oxidation to generate 2 bonds to oxygen. So this would be, in this case, formaldehyde. Or carbonyl here. I'm gonna run out of space. I'm gonna go a little closer. Our next oxidation would be a carboxylic acid. And then finally, carbon dioxide is our like fully oxidized state. Every bond from carbon is to an oxygen here. For oxidations and reductions in this class, we are mostly going to be focusing on this area here, this kind of alcohol, ketone aldehyde, carboxylic acid area. All right, so the easiest way, and we're going to start off with reductions, and then we'll do oxidations later. So reductions would be going in this direction. Versus oxidations be going in this direction. So for instance, a reduction would be something like taking acetone here. We're going to throw in a very simple reducing agent that you guys have seen before. So you could throw in H2 and platinum. We think of this as reducing double bonds. We currently have a double bond. So this would reduce our carbonyl down to an alcohol here. So this is our simplest reduction. The issue with this using H2 is that it is not very selective. It loves to reduce, so if we throw in H2 with, for instance, this molecule here, we are going to reduce both our OH as well as our alkene here. So in order to get a little bit more selectivity, we're going to use a different reagent. And there's two of them that we'll use a bunch. The first one is, let's take the same molecule. Sodium borohydride, so NaBH4. And methanol. And this is going to let us selectively reduce just our aldehyde or ketone. The way this reagent works is it's what's called a hydride donor. So this BH4 here is going to donate one of these hydrides. So we're moving both this proton as well as the two electrons there. And then lastly, we can pick up a proton from methanol. To generate an alcohol here. All right, so fairly straightforward. We have another reagent which is somewhat similar. but it's going to be a little bit more powerful. So this is generally referred to as our mild reducing reagent. Our more powerful reducing agent is going to do the same thing in this case, but in another example, it'll do more reductions. So let's take this same example here. So instead of adding in sodium borohydride, if you add in lithium aluminum hydride, this is often going to be abbreviated as just LAH, followed by water. This is also going to do the same reduction. The difference is going to be when we start dealing with carboxylic acids and esters. This reagent will produce them versus sodium borohydride. Because it's a little bit softer, it will not. So just to kind of throw these all together, if I add in sodium borohydride, this is one step for this one, and methanol, I can do the exact same reaction. Versus H2, which is just going to completely reduce everything. And give us just our carbon chain. So this part also got reduced. All right, so the part where this becomes different is when we're starting to deal with carboxylic acids and esters. So let's look at the carboxylic acid first. We're still using that chart we used before. So when we take a carboxylic acid and we throw in lithium aluminum hydride, or LAH, this will reduce all the way back down to our alcohol. So we temporarily went through our aldehyde oxidation state and then ended up fully reduced down to this alcohol here. If we can also do this with H2, it is also a good reducing agent. But like before, it'll reduce absolutely everything. Our milder reducing agent, which was sodium borohydride, is not going to be strong enough to reduce a carboxylic acid, and this is just going to give us no reaction. So when am I going to care about this? If we have both on a molecule, so let's say we had something like this here and we throw in LAH. Also, with these reducing agents, you're going to always assume that they're in excess. They tend to, once they reduce one thing, it's easier for them to start reducing everything. So you never would try to add in one equivalent of one. It's not selective enough to pick up on one carbonyl over the other. So it'll just start reducing everything in your molecule. So if I added in LAH with this compound, which has both a carboxylic acid let's make a little note here about what I just said. So we have both a carboxylic acid and an aldehyde here. Our strong reducing agent doesn't really tell the difference between them. It's just going to fully reduce both of these down to alcohols here. Alternatively, our softer reducing agent which doesn't have the ability to reduce a carboxylic acid, so throwing in sodium borohydride. He's only going to be able to reduce our aldehyde. And this will give us some selectivity. So this can't reduce carboxylic acids. Or esters.
Can it reduce ketones?
Yeah, it can reduce ketones. So ketones and aldehydes are kind of in like one group, and then carboxylic acids and esters are in the other one. So if we had the same thing without that H on there, this would get us to this compound here. Versus on the left, or on the top, we go still fully down to just alcohols.
Why there's not an alcohol on the carboxylic acid position? For the top one.
Why is there not an alcohol there?
Yeah, on top. There's one already, and then shouldn't be there another one on the carboxylic acid position?
You mean like this?
Yes.
That's just a rotational isomer. It's the same thing. You're just pointing it up versus pointing it down.
Okay.
Like, that's the same molecule. Does that make sense?
Yes, thank you.
You're welcome. Okay, let's talk about esters a little bit because they're a little more complicated. So, like we said, sodium borohydride is not going to have any effect on these. You could write no reaction. You could redraw the molecule either. It's fine. If we add an LAH, we're going to be able to reduce this. This is a much stronger reducing agent. The way these end up getting reduced, and we'll go through a mechanism for them, but you're essentially going to break this into two different alcohols. So you're going to break it down here. It'll initially turn this into an aldehyde and an alcohol, and then this aldehyde will get yet again reduced to having two alcohols at the end of this. So when you're reducing esters, you're going to end up generating two alcohols. One of them is going to be coming from our carbonyl side. The other side is coming from just our alcohol or ether side of this ester here. So let's take another example, kind of walk through a full mechanism for it, and then maybe do one or two just to kind of hammer home the point. So lithium aluminum hydride is also a hydride donor. It's going to have one of its hydrides come in, attack at this carbonyl, push our electrons up to the oxygen, from this point here, our electrons on this negatively charged oxygen are going to try to come back down to reform a carbonyl. And when they do so, it's going to push out our first alcohol. From this point here, we're going to kind of ignore this ethanol for the moment. We're going to have this aldehyde interact with another equivalent of our LAH, so another lithium aluminum hydride. We'll donate a hydride. Our last step is throwing in water. Which will give us a bunch of H pluses that we could pick up to give us the two alcohols of our product. So as I kind of talked about earlier, I like to think of this as breaking this bond down here and generating an alcohol on either side of it. Okay, let's kind of summarize this a little bit. Or let's just do another one. So if I have something that's more complicated, for instance, this molecule here, throwing in LAH, We're going to be breaking down this position here. If you like to think of this in 2 steps, you're initially going to break this apart into an aldehyde and a alcohol. Your aldehyde is going to yet again get reduced. Into benzyl alcohol plus isopropanol here. We again get some selectivity here. So if we take a ketoester, something that has both a ketone and an ester on it, and throw in our soft reducing agent, sodium borohydride, we will selectively reduce this at just our ketone position. Versus if we take this in LAH, we're going to do our hard reduction. If we want to think of this in 2 parts here, we would initially break this bond we could reduce both of the carbonyls on the left molecule to alcohols plus our ethanol. All right, let's do one that's slightly more complicated. And then we will take a little break. So let's look at this one, which has an internal ester in it. So ester is part of this ring here. If we were to throw in sodium borohydride, in methanol, this is only selective for the aldehydes and the ketones. So we don't really have to worry about our ester for this one. This is just going to reduce our ketone down to an alcohol. But then when we throw in LAH with this molecule, this is going to reduce both. So I'm going to keep doing the same way I have been doing it. So we're going to break this and just reduce this bond first. Our alcohol is still attached, so you have to draw it in. from this point, we are just going to reduce, and we should probably make sure we have the same amount of carbon. So 1, 2, 3, and then an alcohol. We reduce both of our carbonyls. And we'll be able to get this product from the reaction. All right, we're going to take about a 7-minute break. So we're going to meet back here at 10:05 to talk through more material from this chapter. So a little bit of a break, stretch your legs out, etc. So see you guys soon. All right, so we are going to talk about the Grignard reaction. The Grignard reaction it's essentially the exact same reaction we just talked about. The biggest difference is that going to be, so our lithium aluminum hydride reactions, when we're adding in to a ketone, what we're essentially doing is taking what's called a hydride equivalent, so an H- equivalent, we pick up a proton somewhere, generate an alcohol, and we've added this hydrogen on. What we're going to do is the Grignard reaction is going to be the equivalent of a carbon nucleophile. Putting little quotations around this one also. Coming in, doing the exact same action, you're going to pick up an H plus somewhere. And now we're going to be adding carbons instead of just adding that H here. So, like with our reductions, where we weren't able to just use hydride, we had to use something, a carrier. So lithium aluminum hydride or sodium borohydride. We can't just use carbon as a nucleophile. It's too strong of a base. Same thing with sodium or with just hydride. We're going to use what's called a Grignard reagent. So a Grignard reagent is going to be something that looks like this here. We have both a magnesium and a bromide. To give you kind of a little bit more detailed look at this, we have a CH2 on the end with a negative charge. And then we're going to have two counter ions. So we have a magnesium, which is a 2 plus, and then a Br, which has a -1. So we get two negatively charged, one from our carbon, one from our bromine, the other one from our magnesium. And this all kind of stabilizes this molecule here, prevents it from acting as a base, lets this act as a nucleophile. So when this interacts with a ketone, we would draw this lone pair in that are on our carbon here. They can attack at our carbonyl site. We are going to add these three carbons on the bottom. So 1 bond, 2, 3 here. And then the last step of this, you could be throwing in water, so some sort of H plus. To give us our alcohol here. So we're still doing a reduction when we do this. We're going to go from a ketone to an alcohol here, but we're also adding carbons at the same time. So to kind of put this side by side with lithium aluminum hydride. This will do a reduction, and we added a hydrogen to this position. I do this with the Grignard. So let's do a 2-carbon Grignard. We're still doing that reduction. But we've now added carbon. So it's a new way for us to make carbon-carbon bonds. Up till this point, the only way we knew how to do it was with an alkyne and an NH2. And halogen. Alternatively, now we can do something like having an aldehyde here or a ketone. To generate this product here. So this gives us a little bit more in our toolbox in terms of generating these carbon-carbon bonds, which will be helpful when we talk about synthesis probably Monday. All right, so yes, can it be as long as you want? Yeah, you can really do whatever you want with these reactions. So one you guys will, if you take the lab along with this class, probably see a lot is phenyl magnesium bromide. So reducing down on alcohol, adding an aromatic ring. I don't know, I'm just kind of making some stuff up as we go. Whatever size compound you want to have. You can pretty much add as anything you want with this. So as long as it has an MGB on the end, whoops, that should not be 5 bonds of carbon there. You reduce under alcohol. This can attach as big of a chain as you want to it. Like with esters before, they are going to be a little bit more complicated. So when we threw in LAH, I'll make the H blue. When we're making this compound here on our first step, we would add 1 hydrogen on here our second step, we're going to end up adding a second one. Eventually water will come in, so I'm just going to add H+. What we ended up generating was this here, where we've added 2 hydrogens from LAH. So when we use a Grignard on an ester, we're going to add 2 carbon equivalents in the exact same fashion. So if we take the exact same molecule and instead throw in ethyl magnesium bromide, our product is going to be almost identical as it was when we threw in lithium aluminum hydride. We're going to end up breaking down this bond here, forming an alcohol plus another alcohol over here. The difference is that we're going to end up adding 2 equivalents of our Grignard to this center. Just like before, when we threw in LAH. And we got these 2 hydrogens. In the Grignard reaction on top, what is the last product? Like this guy? Oh, that's just ethanol. So let me make it look a little prettier. And that came from this here. All right, so this is our double Grignard addition. Let's talk through it. If we have an ester and we add in Grignard, nope, not a Grignard. Let's use this ethyl Grignard here. We'll have the 2 electrons on this terminal carbon. They can come in and attack here. We'll add 2 carbons to this position, make an O-. Our O- will then come down to kick out this ethanol here. We're going to make a ketone originally. Plus our negatively charged version of ethanol. From here, we are still in solution with the Grignard, which reduces ketones. Oops, that's 3 dots. If we take this same example here, or the same ethyl Grignard, it can do an attack, kick our electrons upward. We'll generate this negatively charged oxygen along with our ethanol one that we still had previously. Our last step, we're throwing in water. We're just going to have a lot of H plus floating around. Which we can pick up to generate the alcohols for our product. Okay, let's take a look at the 2 examples we talked about with LAH. This is not really a selective reaction. So we had an ester and an ether together. We threw an LAH. Too many carbons. What am I doing here? So split down this center. Oh. There we go. That's what I want. Reduce this to an alcohol, reduce this to an alcohol. Ethanol is kind of our byproduct from our ester cleavage. If we do the same thing with the Grignard, let's do, I don't know. This Grignard here, everywhere that we've reduced top is now going to get, instead of getting a hydrogen, so this is where our hydrogens ended up from our Grignard or from our production. We're now going to get the addition of carbon groups to this position. Okay, so we'll probably talk more about Grignards in the future. They're very useful. I'm going to skip past I'm going to move on to something else for the moment, and then we will kind of probably touch back at them at the end of the week. And we'll see them a little bit tomorrow in chapter 13 also. So let's kind of talk about the opposite reaction. Everything we've been doing right up till now has been reductions. Let's talk about some oxidation reactions. The book kind of put these at the end, but I'm going to talk about them, and then we'll do a few other reactions to make alcohols into better leaving groups. But I want to talk about these first. So they are pretty straightforward. I'm not going to focus on a mechanism for these because they are pretty complicated. I just want you guys to know what reagents do what. So if I have a primary alcohol here, this alcohol has 2 hydrogens on it. And the number of hydrogens is going to determine your ability to oxidize. So because there's 2 H's, this has the potential to oxidize twice. There's going to be 2 oxidizing reagents that we're going to deal with in this class. The first one is what's referred to as PCC. It is a, what is it? It's pyridine chromic acid chloride. You don't need to know that. You're just going to see it as PCC. What this will do is this will do a single oxidation. You can think of this as your mild oxidizing reagent. So for this alcohol here, a single oxidation would take us to an aldehyde. You've created one more bond to carbon. Alternatively, well, not alternatively, but similarly, if we take this secondary alcohol here, we're using our single oxidation or a mild oxidant. This is still going to do a one-step oxidation, take us to a ketone here. Our stronger oxidizing group is going to be chromic acid, NH2SO4, and water. So chromic acid is Na2, Cr2O7, NH2SO4, and water. And what this will do is this is going to fully oxidize. So we had 2 hydrogens here. This could oxidize initially to an aldehyde and then further down to a carboxylic acid. This is not going to break any bonds. So if I have a secondary alcohol, I throw in chromic acid. Because there's only one hydrogen here, it can only do a single oxidation. And you're still going to get just a ketone here. So like with our reductions, let's put these on the same molecule and kind of talk about what happened. So if I had this here and I threw in PCC, this is our single oxidizing reagent. It's going to oxidize once at each of these positions. giving us an aldehyde and a ketone. If we threw in our stronger oxidizing reagent, and this will let us oxidize up to this carboxylic acid on the right. On the left, we only had one hydrogen, so we're only able to generate the ketone here. Something to note is that you are required to have hydrogen there in order to oxidize. So if you have something like a tertiary alcohol here, you throw in either PCC or Na2Cr2O7. Because we have no hydrogens on here, this is just going to end up as no reaction. So these are all carbons. We have nothing to oxidize. We're not going to break a carbon-carbon bond. This is just going to be our product. And you can throw those all together. Oh god, I gotta come up with something. So, big version of this. We've got tertiary, secondary, primary here. 2 protons, 1 proton, 0 protons to pull off. With PCC, you'll do a single oxidation. Again, there's nothing to do on the tertiary center. With our chromic acid, you're going to fully oxidize. As much as you can. So the primary one will oxidize twice. Secondary one will still only be able to oxidize once. And then the tertiary one will not be able to oxidize at all. All right, let's talk a little bit about alcohol as a leaving group. No, I'm kind of treating this as 2 different reactions. So this would be one reaction over here. This would be a different reaction. I just didn't redraw the starting material. So with PCC, we're going to lead to this product. With chromic acid, we're going to lead to this product here. So you only get one product. I just had 2 different reactions that are coming from the same starting material. Okay. Alcohols as leaving groups. So And alcohol is notoriously bad as a leaving group. I'm going to abbreviate leaving group to LG. If you throw in NaCl, this is going to do nothing. It's not going to leave. It likes making that bond there. OH minus isn't particularly stable. It also can act as a nucleophile, so it would just leave and come right back. In order to make this a good leaving group, we got to do a couple of different things. One option is to protonate it. And this is kind of your SN1 option. You guys have known this for a while. So if I take, instead of NaCl, if I take HCl, oh, no. I can make what is essentially water. Water does want to leave, so it will. Make a carbocation. We've lost our stereochemistry. Cl minus can come in. We can chlorinate. So this is our straightforward version. I mean, this is our SN1 version. We've talked about this for at least a semester now. You guys should be fairly familiar with this one. A different way to make an alcohol a good leaving group is to attach something that has resonance to it. So we're going to talk about these tosyl chlorides. As well as a few different ways to do it. So another option is to take an alcohol, and let's say we want to do an SN1. We are going to add in, you'll often see it abbreviated as TSCl. What this is this reagent here. Actually, I'm going to draw it up here. You're also going to use what's called pyridine. You might see it as PY, PYR. And this is just a mild base. So our tosyl chloride is a pretty good electrophile. Water is going to want to attack it. Our electrons are going to get kicked up to an oxygen, back down, and kick out one of these chlorines, or the chlorine. Yes, you need to know this mechanism. From this point, our pyridine is going to grab this proton to give us a stable molecule. This is often abbreviated as just OTS. And you might often see this mechanism. I'll draw out a shorter version of it in a minute. So from this point, we can have something like NaCl. Come in, our Cl can attack. We're going to do an SN2. And we're going to actually be able to invert our chemistry. So this lets us actually do an SN2 on this compound here. The short version of this mechanism. You can attack this TS. We'll lose a proton. And then Cl minus can do an SN2. So this would be the two-step version of this. You could also swap out, if you wanted to, your NaCl for a base instead and do eliminations. We'll talk a little bit about that later on. I'm going to finish up with talking about two different reactions which do something very similar. One of them is going to generate a bromination version of this, and the other one's going to generate this same chlorination version. So the first one's going to use a compound called thionyl chloride. Or SOCl2, as you'll see it. Listed most of the time. So SOCl2 in pyridine is going to behave similarly. We're going to have our oxygen come in, do an attack. Pyridine can pull off this proton here. We are going to lose one of our chlorines. And then from this point, that chlorine that we lost will come in, kick out this oxygen compound here. And we're going to generate our SN2 product. So very similar reaction to what we were doing with thionyl chloride, except we're doing it in one step now. So all right, the last one that we're going to talk about is it's essentially the exact same thing. The biggest difference is going to be you're going to use what's called PBr3. And this is going to let us brominate instead of chlorinate. So very similar. This mechanism is pretty straightforward. It's kind of a simplified version of the other two because you don't really have any carbonyls you're attacking. So we're going to take an oxygen. It's going to attack the potassium. Pick out one of these bromines. The bromine that was kicked out can then come in. Do an SN2. And we'll form our product. Okay, so we're going to stop here. This is the end of everything we're going to talk about from chapter 12. So I will see you guys in recitation today. There's still one more person who needs to take the exam. After that happens, I will release a key for it. Scores should all be posted on Canvas already. If anyone is interested in talking through their exam, I'm happy to meet with you and go through it. So I will see you guys in about either 15 minutes or an hour and 15 minutes. So have a great day.